March 24, 1945. The Rhine River flows dark and swift beneath a gray European dawn. Its waters carrying the detritus of a dying empire, pieces of Wehrmacht pontoons, scattered artillery shells. The ghostly remnants of Adolf Hitler's Atlantic Wall, now crumbling 300 miles to the west. On the eastern bank, Oberst Heinrich Müller adjusts his field glasses and watches something that defies every principle of German military engineering he has learned in 23 years of service. Across the water, American soldiers are assembling what appears to be a bridge from a child's construction. Set prefabricated steel panels clicking together with mechanical precision. Each section identical to the last. Rising from the riverbank like some industrial organism growing at impossible speed, the sound reaches his ears before his mind can process what his eyes are seeing, the rhythmic hammering of steel on steel. Not the careful, methodical placement of proper bridge construction, but something faster, more urgent, almost musical in its mechanical repetition. Müller has destroyed 17 bridges in his retreat across western Germany. Each one took his engineers days to properly demolish, carefully placed charges calculated to ensure complete destruction of load-bearing structures. And now, 6 hours after the American advance guard reached this crossing point, they are driving trucks across a fully functional bridge where yesterday there was only flowing water. The story of this moment begins not with the bridge itself, but with a fundamental misunderstanding that would prove fatal to the Third Reich's defensive strategy. German military doctrine, refined through 2 world wars and rooted in the methodical precision of Prussian engineering tradition, viewed bridge construction as a deliberate, time-intensive process requiring specialized equipment, detailed planning, and extensive preparation. When Wehrmacht engineers destroyed a bridge, they calculated that Allied forces would require weeks, perhaps months, to restore a crossing capable of supporting mechanized divisions. This assumption formed the cornerstone of Germany's defensive planning as Allied armies approached the Rhine, but the Germans had never encountered American industrial thinking applied to warfare. They had never witnessed the marriage of Henry Ford's assembly line philosophy with the unlimited resources of a continent that had transformed itself into history's most powerful war machine. They had never seen what happened when American engineers, trained not in the methodical traditions of European military academies, but in the rapid-fire improvisation of industrial expansion, approached the ancient problem of river crossing with the same mentality that had built the Empire State Building in 410 days. The prefabricated steel panels that Oberst Müller watched through his field glasses were Bailey Bridge components, each piece precisely engineered to be identical, interchangeable, and capable of assembly by ordinary soldiers with minimal training. Where German engineers thought in terms of custom solutions for specific crossings, American engineers thought in terms of mass production standardized components that could span any gap, support any load, and be assembled anywhere with nothing more than muscle, determination, and American steel. What the German high command failed to comprehend was that their enemy approached warfare not as a chess match of careful moves and calculated positions, but as a manufacturing problem to be solved through overwhelming production and relentless efficiency. While German factories struggled to produce specialized bridge-building equipment in small quantities, American shipyards were completing Liberty ships at an average rate of 3 every 2 days, 2,710 vessels between 1941 and 1945. Each one built with the same standardized efficiency that now characterized American military engineering. The philosophical difference was profound. German military thinking, shaped by centuries of European warfare, where resources were limited and every decision carried enormous strategic weight, emphasized careful planning, methodical execution, and the preservation of valuable equipment. American military thinking, born from a nation that had laid railroad tracks across an entire continent and built skyscrapers in Manhattan swampland, emphasized speed, redundancy, and the assumption that whatever was destroyed could be rebuilt, bigger and better. In a fraction of the time, this divergence became painfully apparent to German defenders as Allied forces advanced across Europe. Wehrmacht engineers would spend precious hours, sometimes days, preparing demolition charges to completely destroy a bridge crossing. They would use scarce explosives, withdraw valuable equipment, and sacrifice defensive positions, all based on the reasonable assumption that bridge reconstruction would provide them with weeks of operational breathing space. Then, often less than 24 hours later, American vehicles would be crossing a newly constructed span that appeared, from German perspectives, to have materialized from nowhere. The Bailey Bridge system embodied everything that German military engineering found incomprehensible about American warfare. Each bridge component was produced by the thousands in American factories, shipped across the Atlantic in Liberty ship cargo holds, and stockpiled at forward supply depots where they waited for deployment. When American forces encountered a river crossing, they didn't dispatch specialized engineers with custom equipment. Instead, ordinary combat soldiers unpacked standardized components and assembled them according to simple, illustrated instructions that reduced complex engineering to basic construction tasks. A standard Bailey Bridge could be erected by 50 men in 4 hours without cranes, specialized tools, or engineering degrees. The system was so thoroughly standardized that components manufactured in Detroit would fit perfectly with panels produced in Pittsburgh, creating spans that could support Sherman tanks, supply trucks, and entire mechanized divisions. More importantly, from an American perspective, Bailey bridges were expendable. If German artillery destroyed a crossing, American engineers simply unpacked another set of components and built a replacement, often at a different location, forcing German defenders to constantly adjust their fire and waste precious ammunition on targets that could be replaced faster than they could be destroyed. This expendability represented perhaps the most profound cultural shock for German military observers. European warfare had always been characterized by the careful preservation of valuable resources. Bridges were substantial investments, built to last for generations, their destruction representing significant material losses that required substantial time and resources to replace. The German military mind, trained to view every tactical decision through the lens of resource conservation, simply could not comprehend an enemy that treated major engineering projects as disposable items. The contrast became starkly apparent during the Rhine crossings of 1945. German defenders had spent months preparing defensive positions based on the assumption that the Rhine River would provide a substantial natural barrier, buying them precious time to reorganize their forces and establish new defensive lines. They systematically destroyed every bridge crossing, confident that Allied forces would require extensive preparation time to establish bridgeheads on the eastern bank. Instead, American forces treated the Rhine like any other tactical obstacle. Within hours of reaching the western bank, combat engineers were assembling pontoon bridges, Bailey spans, and treadway crossings at multiple points simultaneously. The speed of construction was so rapid that German artillery observers found themselves unable to effectively target bridging operations by the time they had ranged their guns on one crossing site. American engineers had completed their work and moved to the next location. The 85th Engineer Combat Battalion set a record that exemplified this new approach to warfare. Their pontoon bridge near Worms, completed in 6 hours and 15 minutes on March 28, 1945, stretched over 1,152 feet across the Rhine and could support the heaviest Allied vehicles. The construction time was so rapid that German defenders had insufficient opportunity to organize effective countermeasures. More importantly, the Americans were simultaneously building multiple crossings, making it impossible for German forces to concentrate their limited artillery and air assets against any single target. What emerged from these operations was not just tactical success, but a fundamental demonstration of industrial warfare's transformative power. The Bailey Bridge became a symbol of American material abundance, a steel and concrete manifestation of a nation that could mass-produce solutions to any military problem. Each bridge component represented thousands of hours of American factory labor, the output of blast furnaces in Pittsburgh and rolling mills in Gary, Indiana, the collective effort of millions of workers who would never see the rivers their products would span. The psychological impact on German forces was devastating. Soldiers who had been trained to think in terms of calculated resource allocation and careful tactical planning found themselves facing an enemy that seemed to possess unlimited supplies and infinite manufacturing capacity. Every bridge they destroyed was replaced by two more. Every defensive position they carefully prepared was bypassed by new crossings that appeared overnight. The very foundations of German military thinking, assumption that warfare was a struggle between finite resources, requiring careful allocation, crumbled. In the face of American industrial abundance, German prisoners of war frequently expressed amazement at the sheer quantity of American equipment. They had been conditioned to expect careful, methodical operations where every tank, every artillery shell, every bridge component was precious and irreplaceable. Instead, they encountered supply convoys that stretched for miles, equipment dumps that contained more material than entire German divisions possessed, and engineering operations that treated major construction projects as routine maintenance tasks. The Bailey Bridge became the perfect embodiment of this abundance. To German observers, accustomed to thinking of bridges as permanent infrastructure, requiring specialized engineering and substantial investment, the sight of American soldiers casually assembling heavy-duty river crossings from prefabricated components represented a kind of material magic. The bridges appeared solid, capable of supporting the heaviest vehicles, but they were assembled with the same casual efficiency that American soldiers displayed when setting up field kitchens or communication networks. This casual efficiency masked sophisticated industrial planning. The Bailey Bridge system represented years of engineering development, testing, and refinement. The standardization that made field assembly so simple required extensive factory coordination and quality control. The steel that formed each panel had been precisely calculated to provide optimal strength-to-weight ratios. The interconnection systems had been designed to distribute loads across multiple structural elements, creating bridges that were actually superior to many permanent installations. But German defenders saw none of this sophisticated background. They saw only the end result, bridges that appeared overnight, assembled by ordinary soldiers, strong enough to support mechanized divisions, and expendable enough to be abandoned without strategic concern when tactical situations changed. The cognitive dissonance was profound. How could something so casually constructed be so functionally effective? How could an enemy treat major engineering projects as disposable assets? The answer lay in American industrial philosophy, which had developed during decades of continental expansion and urban construction. American industry had learned to standardize complex processes, mass-produce sophisticated products, and treat individual items as interchangeable components in larger systems. The Bailey Bridge applied this industrial thinking to military engineering, creating modular construction systems that could be deployed anywhere, assembled by anyone, and replaced at will. The steel components that formed each Bailey Bridge carried with them the essence of American industrial power. The metal had been forged in blast furnaces fed by coal from Pennsylvania and iron ore from Minnesota. It had been shaped by rolling mills powered by hydroelectric dams across the Tennessee Valley. It had been transported by railroad networks that spanned a continent, loaded onto ships and ports that could accommodate the world's largest vessels. and delivered to combat zones by supply systems that dwarfed anything in military history. Each bridge panel represented not just a piece of military equipment, but a fragment of an industrial civilization that had transformed itself into history's most powerful war machine. When German soldiers saw American engineers assembling Bailey bridges, they were witnessing the final expression of a production system that had built transcontinental railroads, erected skyscraper cities, and turned entire regions into manufacturing centers dedicated to military production. The psychological impact extended beyond immediate tactical considerations. German military doctrine had always emphasized the importance of controlling key terrain features, bridges, mountain passes, river crossings, based on the assumption that such positions provided lasting strategic advantages. The Bailey Bridge system rendered this doctrine obsolete. Key terrain could no longer be permanently denied to American forces because American engineers could create their own key terrain wherever tactical situations required. This capability transformed the nature of defensive warfare. German commanders found themselves unable to predict where Allied forces would cross rivers or establish bridgeheads. Traditional defensive planning, which relied on concentrating forces at likely crossing points, became ineffective when the enemy could create crossing points at will. The strategic value of natural obstacles was diminished when those obstacles could be rapidly overcome through standardized engineering solutions. The speed of Bailey Bridge construction also meant that German forces had insufficient time to organize effective countermeasures. Traditional military engineering provided defenders with advance warning of enemy intentions, the movement of specialized equipment, the concentration of engineering units, the establishment of construction sites. Bailey Bridge components, however, were so compact and standardized that they could be concealed until the moment of assembly. German observers might see routine supply convoys passing through forward areas, unaware that those convoys carried the components for major river crossings. The element of surprise was particularly devastating during the Rhine campaign. German defenders had positioned their artillery to cover traditional crossing sites, but American engineers often selected locations that offered no permanent infrastructure advantages beyond proximity to main supply routes. The ability to create effective bridges at seemingly random locations meant that German defensive fires were constantly misdirected, wasting scarce ammunition on empty river crossings while actual bridging operations proceeded unhindered at unexpected locations. The material abundance that made Bailey Bridge operations possible also demonstrated the fundamental disparity between American and German war production. While German industry struggled to produce sufficient quantities of specialized military equipment, American factories were mass-producing standardized components that could be deployed for multiple purposes. The same industrial capacity that produced Bailey Bridge panels also manufactured Liberty ship components, aircraft parts, tank armor, and artillery shells, all using standardized production techniques that maximized efficiency and minimized resource requirements. This standardization created synergistic effects that multiplied American military capabilities. Factories that produced structural steel for bridges could rapidly convert to manufacturing tank components when tactical situations required. Workers trained in precision assembly techniques could transfer their skills between different military production programs. Supply systems designed to handle standardized components could efficiently distribute diverse military equipment using common transportation and storage methods. German industry, by contrast, remained fragmented into specialized production centers that could not easily adapt to changing military requirements. The precision engineering that had made German products famous in peacetime became a liability in wartime, when rapid production and battlefield adaptability were more valuable than technical perfection. German engineers continued to design custom solutions for specific problems while American engineers created standardized systems that could address entire categories of military challenges. The Bailey Bridge exemplified this difference in approach. Where German engineers might design a specific bridge for a particular river crossing, calculating exact load requirements and environmental conditions, American engineers created a modular system that could span any reasonable gap with predetermined load capacities. The American approach sacrificed some theoretical efficiency in favor of practical versatility, but the versatility proved far more valuable in fluid combat situations. The standardization also extended to training and deployment. German bridge construction required specialized engineers with extensive technical education and experience. Bailey Bridge assembly could be taught to ordinary infantry soldiers in a few hours of instruction. This democratization of engineering capability meant that American forces could conduct bridging operations wherever tactical situations required, without waiting for specialized units to become available. The training materials for Bailey Bridge assembly reflected American industrial thinking. Instead of comprehensive technical manuals requiring engineering expertise, American soldiers received simple illustrated instructions that reduced complex construction to step-by-step procedures. The components themselves were designed to be foolproof. They could only be assembled correctly, making engineering errors virtually impossible even under combat conditions. This simplification of complex processes represented a fundamental American innovation in military organization. By reducing sophisticated tasks to standardized procedures that could be performed by minimally trained personnel, American forces could deploy advanced capabilities across their entire organization rather than concentrating technical expertise in specialized units. The result was a military force that could perform complex engineering tasks at any level of command. From individual soldiers to entire army groups, the speed advantages of this approach became apparent during sustained operations. While German forces had to carefully husband their limited engineering resources, American units could conduct simultaneous bridging operations at multiple locations without compromising their overall engineering capability. The redundancy meant that American forces could afford to lose bridges to enemy action without significant operational impact. Replacement bridges could be constructed faster than German forces could destroy existing ones. This redundancy also enabled American forces to use bridges tactically rather than just strategically. Bailey bridges could be constructed for temporary use during specific operations, then dismantled and relocated as tactical situations evolved. German forces, accustomed to viewing bridges as permanent infrastructure that must be defended or destroyed, found themselves unable to predict American movements because American engineers could create or eliminate crossing points based on immediate tactical requirements. The tactical flexibility extended to bridge design itself. Bailey components could be configured in multiple ways to create bridges with different load capacities, spans, and structural characteristics. A single stockpile of standardized components could produce bridges suitable for infantry crossings, light vehicle traffic, or heavy tank movements, depending on tactical requirements. This configurability meant that American engineers could optimize each bridge for specific missions without requiring different types of equipment or specialized components. The psychological impact of this flexibility was profound. German defenders could never be certain what type of crossing American forces would construct at any given location. Artillery and air attacks had to be planned without knowing whether the target would be a temporary infantry bridge that could be quickly replaced or a heavy-duty tank crossing that might represent a major strategic threat. The uncertainty forced German commanders to disperse their defensive efforts across multiple potential targets, reducing the effectiveness of their limited resources. The Bailey Bridge also demonstrated American attitudes toward military equipment that differed fundamentally from European traditions. In German military culture, equipment was expected to be durable, repairable, and preserved for long-term use. American military culture emphasized functionality, replaceability, and adaptation to immediate needs. Bailey bridges embodied this philosophy. They were built to perform specific missions effectively. But they were not expected to last indefinitely or serve multiple generations of users. This disposable mentality enabled American forces to use equipment in ways that would have seemed wasteful to German observers. Bridges could be abandoned when tactical situations changed, rather than defended as valuable assets. Components could be modified or adapted for unexpected uses without concern for preserving their original configuration. The emphasis was on mission accomplishment rather than equipment preservation, a perspective that reflected America's industrial abundance and production capabilities. The environmental impact of Bailey Bridge operations also reflected American industrial thinking. Rather than carefully selecting optimal locations for permanent bridges, American engineers could construct crossings wherever tactical advantages existed, regardless of long-term environmental considerations. The bridges were temporary installations that could be removed after military operations concluded. But during wartime they provided maximum operational flexibility without regard for peacetime infrastructure requirements. This temporary approach enabled American forces to exploit tactical opportunities that would have been impossible with traditional bridge construction. River crossings could be established to support specific operations, then relocated to support subsequent missions. The speed of construction meant that tactical windows of opportunity could be exploited immediately, without waiting for lengthy engineering preparations that might allow enemy forces to organize effective countermeasures. The logistical implications were equally significant. Traditional bridge construction required extensive forward stockpiling of specialized equipment and materials. Bailey Bridge operations could be supported by standard supply convoys, carrying standardized components that occupied minimal transportation space and required no special handling procedures. The logistical efficiency meant that bridging capability could be maintained throughout extended operations without compromising other supply requirements. The modular design also simplified supply planning. Instead of calculating specific requirements for individual bridge projects, American quartermasters could stockpile standardized components that could be configured to meet various tactical requirements. The fungibility of Bailey components meant that supply calculations could be based on general operational requirements, rather than specific engineering projects, greatly simplifying logistical coordination. The maintenance requirements were similarly simplified. Traditional bridges required specialized maintenance personnel and custom replacement parts. Bailey bridges used standardized components that could be repaired or replaced by ordinary soldiers using standard tools and procedures. Battle damage could be quickly repaired by substituting damaged panels with identical replacements, restoring full operational capability without specialized technical expertise. This maintenance philosophy reflected broader American approaches to military equipment. Rather than designing systems that required minimal maintenance, American engineers created systems that could be easily maintained by personnel with minimal training. The emphasis was on operational availability rather than theoretical reliability, ensuring that equipment remained functional under combat conditions even when optimal. Maintenance procedures were not possible. The German reaction to Bailey Bridge operations evolved from initial amazement to grudging respect to profound discouragement. Early encounters with Bailey bridges prompted German engineers to study captured components, searching for design flaws or weaknesses that could be exploited. What they discovered was a system that sacrificed theoretical optimization in favor of practical effectiveness. Bridges that were perhaps not as elegant as custom German designs, but that could be deployed faster, maintained more easily, and replaced more quickly than any European equivalent. The standardization that made Bailey bridges so effective also made them difficult to counter. German artillery observers could learn to recognize Bailey bridge components and predict construction patterns. But the speed of assembly meant that effective countermeasures had to be implemented within hours of initial detection. The modular design meant that partially damaged bridges could be quickly repaired, making them difficult to permanently disable with anything short of complete destruction. German attempts to develop countermeasures were hampered by their own production limitations. While American factories could mass-produce Bailey components by the thousands, German industry struggled to manufacture sufficient quantities of conventional bridge equipment for their own forces. The resources required to develop and deploy Bailey Bridge countermeasures were resources that could not be allocated to other pressing military requirements, creating a strategic dilemma that reflected Germany's overall resource constraints. The broader implications of Bailey bridge operations extended beyond immediate tactical advantages. The system demonstrated American industry's ability to transform complex military problems into mass production challenges that could be solved through standardization and scale. The same industrial thinking that made Bailey bridges possible also characterized American approaches to aircraft production, shipbuilding, tank manufacturing, and ammunition supply, creating an integrated war economy that could sustain military operations at unprecedented scales. This industrial approach to warfare represented a fundamental shift in military thinking. Traditional European warfare had been constrained by limited resources that required careful allocation and preservation. American warfare was characterized by abundant resources that enabled tactical flexibility and operational redundancy. The Bailey Bridge embodied this abundance, providing American forces with engineering capabilities that seemed almost magical to enemies. Accustomed to resource scarcity, the steel that formed Bailey bridge components carried with it the essence of American industrial civilization. Each panel represented the accumulated expertise of American metallurgy, the product of blast furnaces that had been refined through decades of commercial competition and industrial innovation. The precision of manufacture reflected quality control systems developed for mass production, ensuring that components produced in different factories at different times would function together seamlessly. The transportation systems that delivered Bailey components to combat zones represented another dimension of American industrial capability. The components traveled by railroad networks that spanned a continent, were loaded onto ships and ports that could handle unprecedented cargo volumes, and were distributed through supply systems that coordinated the movement of millions of tons of military equipment. The logistical coordination required to deliver Bailey components to specific combat units at precise times represented an organizational achievement that rivaled the engineering accomplishment of the bridges themselves. The human resources required for Bailey Bridge operations reflected American democratic values applied to military organization. Rather than relying on elite engineering units with extensive technical training, the system empowered ordinary soldiers to perform sophisticated construction tasks. This democratization of technical capability meant that Bailey Bridge operations could be conducted by any unit with adequate manpower, making bridging capability available throughout American military organization rather than concentrated in specialized formations. The training philosophy that made this democratization possible represented another American innovation. Instead of requiring soldiers to master engineering theory, Bailey Bridge training focused on practical procedures that could be learned through repetition and practice. The standardization of components and assembly procedures meant that soldiers could develop expertise through experience rather than formal education. creating a military force that could adapt sophisticated technologies to immediate tactical requirements. The flexibility of Bailey Bridge systems also enabled American forces to experiment with innovative tactical applications that would have been impossible with traditional bridge construction. Bridges could be constructed to support deception operations, creating the appearance of major crossings where none actually existed. Multiple bridges could be built simultaneously to confuse enemy intelligence about American operational intentions. Bridges could be deliberately constructed in locations that would draw enemy fire away from actual crossing sites. This tactical innovation reflected broader American approaches to military problem solving. Rather than adhering to established doctrines and procedures, American forces were encouraged to adapt available resources to immediate tactical requirements. The Bailey Bridge system provided the flexibility necessary for this adaptive approach, enabling American commanders to implement innovative solutions that exploited specific operational opportunities. The surprise achieved through Bailey Bridge operations was particularly effective because German intelligence systems were designed to detect traditional military preparations. The movement of heavy construction equipment, the establishment of engineering depots, the concentration of specialized personnel, all the indicators that normally preceded major bridging operations, were absent from American Bailey Bridge deployments. German observers might see routine supply convoys and standard infantry movements, unaware that those activities were actually preparations for major river crossings. This intelligence challenge was compounded by the speed of Bailey Bridge construction. Even when German forces detected bridging preparations, they often had insufficient time to organize effective countermeasures before bridges became operational. The traditional military timeline that allowed for reconnaissance, planning, and coordinated response was compressed to a few hours, forcing German commanders to react to accomplished facts rather than anticipated actions. The durability of Bailey bridges under combat conditions also surprised German forces. The standardized design incorporated redundancy and damage tolerance that enabled bridges to remain functional even after sustaining significant battle damage. Artillery hits that would have disabled custom-built bridges often caused only localized damage to Bailey structures that could be quickly repaired with standard replacement components. This battle damage tolerance reflected American engineering philosophy that emphasized redundancy and maintainability over theoretical efficiency. Bailey bridges were designed to degrade gracefully under stress, with damage patterns that were predictable and repairable. The modular construction meant that battle damage typically affected individual components that could be replaced without compromising overall structural integrity. The repair procedures were as standardized as the construction processes. Damage assessment could be conducted by ordinary soldiers using visual inspection techniques that required no specialized knowledge. Repairs typically involved removing damaged components and installing identical replacements, a process that could be completed in minutes or hours rather than the days or weeks required for custom bridge repairs. This rapid repair capability meant that German forces could not permanently disable Bailey bridges through conventional artillery bombardment. Even direct hits that caused substantial damage could be repaired faster than German forces could organize follow-up attacks. The result was a tactical environment where American bridges remained operational despite sustained enemy fire, providing continuous logistical support for advancing forces. The psychological impact on German defenders was devastating. Soldiers who had been trained to view river crossings as major tactical obstacles found themselves facing an enemy that could create bridgeheads almost at will. The fundamental assumptions that underlay German defensive planning, that natural barriers would provide time for reorganization and counterattack, were rendered obsolete by American engineering capabilities. The demoralization was compounded by the apparent effortlessness of American bridge construction. German soldiers who had struggled with limited equipment and scarce resources watched American engineers assemble sophisticated river crossings with the same casual efficiency they might use to erect tents or dig foxholes. The contrast between German scarcity and American abundance was starkly apparent in every Bailey Bridge operation. The sound of Bailey Bridge construction became a harbinger of German defeat. The rhythmic hammering of assembly crews, the mechanical precision of component installation, the steady progress of spans extending across rivers, all represented the relentless advance of American industrial power that could not be stopped by traditional military resistance. Each bridge was not just a tactical asset, but a symbol of American material supremacy that rendered German defensive efforts futile. As spring advanced across the German landscape in 1945, Bailey bridges multiplied like steel flowers blooming along every river and stream. Each crossing represented not just tactical progress, but proof of a fundamental transformation in the nature of warfare itself. The age of careful resource allocation and methodical military planning was ending, replaced by an era of industrial abundance and rapid technological adaptation that would define military conflict for generations to come. The legacy of Bailey Bridge operations extended far beyond their immediate tactical impact. The system demonstrated that complex military problems could be solved through standardization, mass production, and democratic distribution of technical capabilities. The principles that made Bailey Bridges effective: modularity, standardization, rapid deployment, and ease of maintenance would influence military equipment designed for decades after the wars. Conclusion: the steel components that had spanned the rivers of Europe would find new applications in peacetime construction projects around the world. Bailey bridges would continue to serve in military and civilian roles long after the Wehrmacht's final surrender, providing infrastructure solutions in developing countries and disaster relief operations. The engineering principles that made them effective in warfare proved equally valuable in peacetime applications where rapid deployment and standardized construction were essential. But perhaps the most significant legacy was philosophical rather than technical. Bailey Bridge operations demonstrated that American democratic values could be successfully applied to military organization and technological development. The emphasis on standardization over customization, accessibility over exclusivity, and adaptability over optimization reflected broader American approaches to social and economic organization that would shape the post-war world. The German officers who watched Bailey bridges rise from European rivers in coast 1945 were witnessing more than tactical engineering operations. They were observing the final expression of an industrial civilization that had transformed itself into history's most powerful military force. Through the application of democratic principles and capitalist production methods, the bridges were symbols of abundance, efficiency, and technological innovation that represented everything the Third Reich had failed to achieve despite its claims to industrial and engineering superiority. The hollow sound of boots crossing Bailey Bridge decking became the drumbeat of liberation. As Allied forces advanced into the heart of Nazi Germany, each crossing represented not just military progress, but moral triumph, the victory of democratic values over authoritarian control, industrial abundance over resource scarcity, inclusive innovation over exclusive expertise. The bridges carried more than military vehicles. They carried the promise of reconstruction, reconciliation, and renewal that would transform post-war Europe. In the end, the Germans never understood how American engineers could build bridges faster than they could destroy them, because they never understood the industrial civilization that made such achievements possible. They saw only the steel and the speed, not the factories and foundries, the supply systems and training programs, the democratic values and capitalist efficiencies that made Bailey Bridges inevitable expressions of American power. They fought against individual bridges when they were actually confronting an entire civilization organized around principles of mass production, standardized excellence, and unlimited possibility. The Rhine flows on, carrying new generations toward uncertain futures. But the lessons of those steel spans remain embedded in its banks like foundations waiting for construction. Democracy builds faster than tyranny can destroy. Freedom